In this lesson, we're going to kind of bring it all together and look at applications of these linear equations and how to do problem solving, right? I hate that it's called problem solving because problem, right, has a negative connotation. And they're basically word problems. You're going to be given a scenario of a more or less real world scenario, and you need to translate that real world scenario into some algebra junk so you can solve it. It's actually kind of one of the more important skills in math is being able to apply these concepts to story problems. So here's a basic set of steps for solving any kind of word problem, right? First thing you want to do is just read the problem through carefully, start to finish, nice and slow. You're not doing anything but getting an overall feeling for what's the theme of this, because you're going to start seeing that there are what we call families or themes of questions, questions that are all in the same kind of genre, like movie genres, where you've got, comedies, dramas, westerns, so on and so forth. You've got a certain set of questions that all fall under the same kind of umbrella. And when you identify that theme, it tells you the best technique for solving it. Because we're going to have these general steps for solving these things. But then for each individual family of questions, there are these separate little specific tools that can make your life a million times easier if you know and recognize when to use them. And you recognize when to use them by saying, okay, well, this entire family of questions uses this kind of tool. This family of questions uses this other kind of tool, and so on and so forth. So when you're reading it through, you're looking for that theme, that family. You always want to identify the question that they're asking you to solve, and that becomes your unknown, right? So, and then you want to assign labels to those unknown qualities, i.e., you can have an X, a Y, a Z, or you can use variable letters that make more sense. If there's a question that says, you sold this many adult tickets, this many children's tickets, or you sold a total of 850 adult and children's tickets, and blah 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 blah. How many adult tickets did they sell, and how many children's tickets did they sell? So you're trying to solve for how many adult and children tickets you. Well, rather than X and Y, let the number of adult tickets you're trying to find be A, and the number of child's tickets that you're looking to find be C, right? Use letters that make sense, because then it makes it easier for you to keep track of what the heck they are. When it says write a verbal model, they're basically just saying find all the bits and pieces in there that are talking about what's going on and translate it into some math stuff. Find that hidden equation and solve it. And then the last thing you always want to do is interpret the results and make sure that they make sense. Because sometimes you'll have these real world connotations. You'll do the work and you'll get more than one solution. But one of the solutions doesn't make sense in the real world, usually like negative numbers, because negative numbers don't typically exist in the real world. So you throw that one out and you use the other answer instead. Sometimes both answers are fine and you have to use both answers, but just keep that in mind. So one of the skills that you have to be good at is being able to translate English into math. And we've talked about this before. It's one of those skills that you just want to practice. The sum, we always know, means to add some things. Well, what are we summing? We're summing a number and negative 11. Okay, so a number and negative 11. That's summing a number and negative 11. Remember, the word is always equals negative 15. Negative 15. Find the number. Well, that's pretty easy, right? This is just x minus 15 equals, x minus 15. That's my brain moving ahead, right? I always tell you guys, your brain is too smart and it's moving a step ahead. Equals negative 15. Add the 11, and x equals negative 4. 40 less than, right? So anytime you have a less than, remember you're going to have some stuff, and then you're going to subtract the 40. That's 40 less than. What's it less than? 5 times a number. Okay, so 5 times a number is equals 52 less than. Aha, 52 less than. So something minus 52. 52 less than what? The number, right? It's the same number. A number, the number, so it's x again. So we've got 5x minus 40 equals x minus 52. Of course, subtract x from both sides. 4x minus 40 equals negative 52. Add 40 to both sides, and 4x equals negative 12. Divide by 4, and x equals negative 3. You can see that all the rest of the steps are just the basic solving linear equation stuff that we've been learning over and over and over again. The only extra added bonus to these questions is instead of them just giving us something like this, they're giving us the equivalent in English, and we have to translate it to this. Twice the sum of a number and 6. Well, remember, sum is x plus 6. It's twice that, so you have to do twice the whole sum, is 2 more than is you add, right? So you're going to add 2 at the end, 2 more than 3 times the number. And then just like before, we use our same rules. We got to get rid of the grouping object, so we distribute. We combine like terms on each side of the equation, which there is nothing to do. So now we isolate our variable. I'm going to bring the 2x over here to keep it positive. 12 equals x plus 2. Subtract the 2 from both sides, and 10 equals x, or x equals 10. So let's move on to consecutive integer problems. These things are silly, but they come up a lot in textbooks and classes where they talk about consecutive odd integers, consecutive even integers, and then sometimes just consecutive integers. Well, consecutive just means they come right after each other on the number line, but if they're odd integers, you have to skip one. So, for instance, let's remind ourselves what the number line looks like. Here's 0, here's, right, 1, 2, 3, 4, 5, and down here we could have negatives 1, 2, 3, 4, and 5. So consecutive odd integers would be like 1 and 3, or 3 and 5, right? Because they're in order consecutively, but they're odd, so you got to skip the evens. Just like consecutive evens would be 2 and 4. Obviously, if it was just consecutive integers, it'd be 1 and 2, or 2 and 3, and so on and so forth. Don't forget that they could also be negative, right? So consecutive evens would be negative 4 and negative 2, and so on and so on and so on. Well, we need to be able to generalize this because we can't just say I'm going to use the integers 2 and 4. When it says find the integers, that's what we don't know. So I don't know what 2 is. I'm just going to give it an x, right? I'm just looking for an integer. And then the next consecutive odd integer, I guess I should write this underneath 1 instead, or underneath 3, right? Because it's now an odd. So there's my first odd integer. And then my next one would be over here at 5. Well, I can't call that x because these are two different things. I don't want to call it y because I don't want to introduce a second variable. All right, that's no good. So how can I list 5 in terms of 3? Well, isn't 5 just 3 plus 2? And so this one is just x plus 2. And think about it. 3 is just 1 plus 2. So if this was my x, this would be x plus 2. And it works for all of them. If 2 is x, 4 is x plus 2. So anytime you're doing consecutive odd or consecutive even, it's always going to be x and x plus 2. It's just that simple. So the sum of those two things, x plus 2, because those are my two integers, right? Here's the one that's up, bigger than it. Here's the starting one. The sum of that is negative 188. Find the integers. Well, that's easy. 2x plus 2 equals negative 188. Subtract 2. And 2x equals negative 190. Divide by 2, x equals negative 95. And then, of course, negative 95. And then x plus 2 doesn't go to negative 97. It goes to negative 93. Right? Because you got to add 2 to this. And then double check it. This equals negative 188, so that works. So those are my two consecutive integers, negative 95 and negative 93. Right? So now we can take it up a step and we can kind of make it a little bit more complex and say 10 times the smallest of 3 consecutive integers is 22 more than 3 times the sum of the integers. Ugh, right? A lot going on there, but we know it's consecutive integers and we know it's 3 consecutive integers. So let's list them, right? So this is going to be my first integer. This is going to be my second integer, and then wouldn't the next one just be plus 4? right? Think about it. If this is consecutive integers, consecutive integers, sorry, not consecutive even integers. So that changes things, right? If they're consecutive integers, then it's just plus 1 and plus 2. For instance, if this was like 14, 15, and 16, those are consecutive integers. You can see that if x equals 14, you put a 14 in here, 14 plus 1 is 15, put a 14 in here, 14 plus 2 is 16, right? So we just have 3 consecutive regular old integers, not odds and evens. Well, 10 times the smallest, all right, so that's just 10x, we know this is the smallest, is 22 more than, all right, so we got to add 22 to something, 22 more than 3 times the sum of the integers. All right, so 3 times the sum of the integers. Well, that's x plus 1 plus x plus 2, and then the plus 22. So we finally set it up, right? So we read it all the way through. We identified it's a consecutive integer question. We know that when we're dealing with consecutive integers, we've got, x plus 1, x plus 2, or if there are odds and evens, it's x plus 2, x plus 4, so on and so forth. So we've identified that. We labeled our unknowns, the x plus 1, the x plus 2. We go back and we reread it in small little bite-sized pieces and we pull out what it tells us. 10 times the smallest of the 3, so that's my 10x, that's my equals. 22 more than, so that's the plus 22 at the end. 22 more than what? 22 more than 3 times the sum of the integers, so 3 times all of the integers added together. We've translated all the bits and pieces. We've now found our quote-unquote hidden equation, right? Because in every word problem, there's a hidden equation that you have to solve. Now that we have that hidden equation, it just goes back to, well, what are your steps for solving that particular equation? Well, this is a typical linear equation. We know how to solve this. We got to get rid of our grouping objects. We can first combine all of this stuff if we want and have, there's 3 x's in here, right? X, and then the 1 plus the 2 plus 3. That's going to make our life a little easier, right? It's always good to clean things up. Now we can get rid of the parentheses by distributing the 3. 10x equals 3 times 3 is 9x. 3 times 3 is plus 9, plus 22. Combine like terms on both sides of the equation, so there's nothing to do over here. There's no x's over here, but the 9 and the 21 gives us 31. Then isolate our variable, move it all to one side, and we get x equals 31. And we're done. We found our 3 integers, right? It's 31, 32, 33. And we could go through all of this and make sure that it works, right? 10 times this is 310. You could add them together, right? And see that you get 96 times 3. Figure out what that is, add 22 to it, and it better be 310. So let's look at some further applications of linear equations. How about something that's a little bit more real world, where we've got a carpenter cuts a 6 feet board in 2 pieces. One piece must be 3 times as long as the other. Find the length of each piece. Okay, so we read it all the way through. It's talking about taking a piece of wood and cutting it, right? We need to identify the question. We need to find the length of each piece. I always say, if you can draw a picture, right? If it's a question that has anything that's kind of visual, draw yourself a picture. So here's my 6-foot board, right? So 6 feet. It's going to cut it in 2 pieces. So here's my 2 pieces. We need to find the length of each piece. Well, I don't know what this is, right? I don't know what this is. But again, I don't want to introduce a second variable, so instead of calling it y, let's think about it that if this is x and the whole length is 6, then doesn't this have to be 6 minus x? Like if this was 2, this would have to be 4. 6 minus 2 is 4. So it's always a good idea to try and label everything in terms of the same variable, because you're going to have to do that eventually in order to solve it. So I've kind of labeled everything, and now I can go back and I can translate everything. One piece must be 3 times as long as the other. All right, well, I don't know which one is longer, but so I could set either one to be the longer one. One piece must be 3 times as long as the longer one. So let's see how this works. Distribute my 3, 18 minus 3x, right? Because you got to do it everywhere. Then we isolate, So we add to the other side. So we get 4x equals 18. Divide by 4. We get x equals 18 over 4, which is 9 halves, which is 4.5. So this would be 4.5. And if you take 4.5 away from 6, you can do that in your calculator, you're left with 1.5 over here. Right? That adds up to 6. Now ask yourself, does it work? Is one piece 3 times as long as the other? Well, yeah, 1.5 times 3 is 4.5. So it works. We found the lengths. All right, let's just say that we thought, remember, it's 3 times as long as the other. So let's say we did it the other way, and we did 6 minus x equals 3x, and see if it still works, right? So we just did 3 times one of them has to be equal to the other. Well, now, it's very simply, we just add x, and we get 6 equals 4x. Divide both sides by 4. We get x equals, right? 6 divided by 4 is 3 halves, which is 1.5. And look at that, 1.5. And then you could plug 1.5 in here and get 6 minus 1.5 gives you 4.5. You see how you still get the same answer. So it doesn't matter which one, because when it says one must be 3 times as long as the other, well, I mean, it doesn't say anything about which one, right? Like it doesn't say the longer one is 3 times one. Even if it does say that, we still don't know which is the longer one. We just arbitrarily let one of the pieces be x. According to my picture, it was the smaller piece, but I could have just as easily drawn that line over here, and then x would have represented the longer piece, right? So my point is don't be afraid to just jump in, translate it, do the work, and get an answer, and then check the answer. As long as the answer works, then you must have done it correctly. Chances are, if you had translated it differently, you probably would have got it right as well. Okay, our last example. For a recent Olympics, the United States won the greatest number of overall medals, followed by China. The United States won 16 more medals than China, and together they brought home a total of 192 medals. How many medals did each country win? Now, I want you to recognize the theme of this question. I don't want you to say the theme is the Olympics. No. In general, one of the biggest types of families of questions that you will come across are what we call mixture questions. And we call them mixture questions because they're mixing 2 different kinds of things. In this case, they're mixing United States medals with China medals, right? It's the medals won in one place. Remember the one that I talked about earlier where if you had adult tickets and children's tickets, that's a typical mixture problem because you're mixing together adult tickets and children's tickets, and then you're talking about how many total tickets you have. You're mixing together the United States medals with the China medals, and that's how many total medals you have, right? So it's a mixture problem, and when we have mixture problems, we tackle them a specific way. We have specific tools, but we still do everything in general the same. We read it all the way through. We identified it. We identified the question. How many medals does each person or does each country win? We need to designate some variables. So we're going to have, how about S for United States, just because I don't want to write U's, equals U.S. medals, right? And C equals how many medals China got? Medals. So now we can go back and we can write down everything and tell us. The United States won 16 more medals than China. So the amount of medals the U.S. won is 16 more than. So plus 16 to China, right? And then they also tell us together they brought home 192. So that means S plus C equals 192. Now, there's a nice little technique for these things, a table technique that I'll show you in another lesson that helps avoid having to have 2 variables. But with mixture problems, you almost always have 2 variables. You can use the table technique, which helps you figure out how to write it all in terms of 1 variable, or just write down what they tell you. They will always give you 2 different equations, and you need 2 equations to solve 2 variables. And then all you have to do is take one of those equations, solve it for one of the variables, i.e. isolate one of those variables all by itself, and then you can use what's called the substitution method into the other equation. So we've got two equations. This one is already solved for s. See how s is all by itself? And because s is all by itself, we can now take this stuff and put it in place of s, because if s equals this junk, then I can put it down here and have c plus 16 plus c instead of s equals 192. Combine my c's, 2c plus 16 equals 192. Subtract the 16 and get 2c equals, what's that, 166? Double check my work, right? 192 minus 16, 176. See, that's why I got to double check. That's why you're not supposed to do things in your head. 176, and then divide both sides by 2 and get c equals, I'm doing it in my calculator because I've learned from my mistake, equals 88. Okay, so we know that China took home 88 medals, and they told us that the U.S. took home 16 more, right? So if we add 16 to it, we get 104. So 104 and 88, and then double check. If you put those two together, that's 192. So we solved it correctly. And that's all I got for this lesson.